So in the last few videos, we've been talking about how you can figure out forces from the potential energy. And in this next set of videos, we're going to take that one step further and actually go from energies directly to equations of motion. And we're going to do that by using the Lagrangian approach. Now I will note that the Lagrangian approach is going to seem a little bit like magic. It's a very different approach from what you've seen before, at least at first glance it is. Well, in a subsequent video, we'll take the time to sort of step back and say, well, how does that connect? Why does that actually work? We're not going to spend a lot of time talking about why it works. If you're really interested in that, I strongly encourage you to take classical mechanics, advanced classical, which is a place where you'd spend a lot more time thinking about why it works. We're going to take a more operational approach and actually instead sort of see that it does work and see how to do it. So in this video, I'm actually going to show you how to do it on a really simple example. And then in subsequent videos, we'll deconstruct why that worked for the simple example and do some more complex examples. Okay, so the simple example I'm going to do is the sort of easiest example I can imagine. I've got a ball that's dropping under the force of gravity, right? And I'm interested in figuring out what the equations of motion are for this. Now, you know what the equations of motion are for this. Immediately, you could say, okay, well, the force, is minus mg in the j hat direction, right? That means that the mass times the acceleration is minus mg j hat, or dividing about the mass, my acceleration is minus g in the j hat direction. Or if I just think about this in terms of x and y, I'd say my equation of motion for this is y double dot is equal to minus g, right? So it's not a very interesting problem. It's one that you know the answer to. But I want to use that problem to illustrate how the Lagrangian approach works. So for the Lagrangian approach, there are really three steps that you need to follow. The first step is you actually need to define what your coordinate system is for the problem. And this is a place where the sort of idea of natural coordinates that we talked about earlier in the semester really becomes very, very powerful, right? So your first step is, what are your coordinates? And you really want to choose coordinates that enforce the constraints for the problem. Okay? The second thing that you need to do once you've figured out the coordinates is you need to write the Lagrangian, right? And the Lagrangian actually is defined as the kinetic energy minus the potential energy. So you're going to write the Lagrangian in terms of the coordinates. Okay? And then finally, once you've done that, you're going to take derivatives or partial derivatives of the Lagrangian in order to figure out what the equations of motion are. And in particular, the partial derivatives you're going to take is you're going to set the partial derivative of the Lagrangian with respect to the position state variables and make that equal to the derivative with respect to time of the partial Lagrangian with respect to the velocity state variables. Okay? So this equation, or in many cases this will be a set of equations, are the equations of motion. Right? So you'll notice there are no free body diagrams drawn here. There don't actually seem to be any vectors involved in this. You're just taking a bunch of derivatives, and somehow that gives you the equations of motion. Let's see how this actually works for this case. So for this case, the coordinates for this, I'm going to say that the only thing I'm interested in is the y position. So my sort of relevant sort of coordinates or state variables are going to be the y position and also the y velocity, right? Because I'm going to need both of those in order to write what the kinetic energy and the potential energy are, right? So my Lagrangian in that case is the kinetic energy minus the potential energy. The kinetic energy is 1/2 mv squared. Well, in this case, v is simply y dot, so 1/2 my dot squared. And my potential energy is going to be mgy. So my Lagrangian will be 1/2 my dot squared minus mgy, right? And then finally, I need to take the partial derivative of the Lagrangian with respect to the position variables, right? So in this case, I've got one position variable, y, right? And I'm going to set that equal to the time derivative of the partial derivative of the Lagrangian with respect to the corresponding velocity state variable, so y dot, and in principle this should be my equation of motion. Well, let's see if that works. What's the partial derivative of, with respect to y, of 1/2 my dot squared minus mgy? Well, if I'm taking the partial, so that's what the left-hand side is here, right? This thing is that. If I'm taking the partial with respect to y, that means I'm holding y dot constant. So my first term is 1/2 m, which is a constant, y dot is a constant squared. The first term is all constant, d by dy of a constant is 0. And my second term, d by dy of mgy, is mg, right? So this whole thing gives me minus mg, right? And then if I go over to the right-hand side, right, I've got this, right? So I've got d by dt of the partial with respect to y dot of 1/2 my dot squared minus mgy. Well, if I'm taking the partial with respect to y dot of this first term has a y dot in it, so I take the derivative with respect to y dot, I'm going to pull down a 2, I'm going to get my dot. Second term, mgy, doesn't have a y dot in it, so that term, when I take the partial with respect to y dot, is 0. Then I take d by dt of my dot is m times y double dot, so this whole thing ends up giving me m times y double dot, right? So I get minus mg is equal to m times y double dot, or, not surprisingly, y double dot is equal to minus g. Okay? Now, you might look at what I did here and what I did here and think to yourself, why are we doing this Lagrangian thing? Okay, and the answer is that for this problem, it's kind of like taking a bazooka to kill a cockroach, right? This is not really necessarily the right tool to use for solving this problem, but it's actually a nice example to give because you kind of know what the answer is initially, and it's easy to work through and get to this point. For things that are more complicated, that involve multiple state variables, as we'll see in a subsequent video, this is actually quite powerful.